Hey, good morning, guys. My name's Alexa Melendez. I am part of group number 3. I am going to be talking about the activities that we did for lab number 6. As you can see on the right side, we did use this, I guess you could say, protector launcher. It's pretty much, I grabbed the image from what they provided for us, just so I can show you what we worked on. I apologize. So as you can see on the left side, the information for table number 1, and on the right side, it's the information that we got as a group all together last, I believe it was like 2 weeks ago, since we did have spring break. So a little breakdown of how we handled table number 1 for the projectile lab is we figured out the muzzle velocity, or the BM. Basically, we needed to know exactly how much the of the launcher was before we started messing with the different angles. So we had to look at 2 different things happening during the same time. It was how fast the ball lands on the floor and how far it travels from the room in the room. So the setup and the unit struggle, which is 0.45 seconds to 1 minute and 30, starting with our initial positions on our 0, which is the beginning. We set our horizontal starting point X and the height of the launcher, which was 90 centimeters. This is just pretty much the information that it's showing you. So it's the initial values, the initial height, the final distance, the gravity, the bridge time, which is the formula, also calculated time, and the component's velocity. And at the very end, for number 4, it's going to be showing you the results. This, I just asked if they could provide a little graph that could show us the information on how it was traveling, and the projectile path, which is going to be the blue line. The red dot is going to be representing the launching point, and the green point is going to be representing the landing point. So this is pretty much what we have. Also, I wanted to make sure that you do know the formula that we did use, which was provided for us. As a group, we all got together and we decided right after we finished using the stuff that they provided for us to start working on it. The calculations were kind of confusing at the beginning. Our TA was great. He helped us out a lot, which was amazing. And also, I believe that's all I have. Thank you so much. You guys have a good day. And like I said, my name's Alexa Melendez. I am part of group number 3. Thank you.
Good evening, everyone. I am Jade Saucedo, and you are watching Physics Force News. Tonight's media coverage, the physics of projectile motion. I'll be breaking this into 2 parts. First, finding our launcher's muzzle velocity, and second, using that velocity to predict landing spots at various angles. For part 1, it's calculating muzzle velocity. Our first goal was to find the muzzle velocity, VM. This is the initial speed of the ball the moment it leaves the launcher. We started with a completely horizontal shot, 0 degrees, to simplify our variables. Our first step was finding the time. Because we can't trust human reaction time with a stopwatch, we calculate flight time using the vertical drop. Our manual gives us the formula T equals the square root of 2yi divided by negative ay. We used a height yi of 0.9 meters and gravity ay of negative 9.8 meters per second squared. As the manual notes, we enter acceleration as a negative so that the two negatives cancel out, giving us a real positive time of 0.43 seconds. Our second step was solving for Vm. Next, we take the average horizontal distance the ball traveled, xf equals 1.44 meters, and divide it by our time. Using the formula Vm equals xf divided by t, we found our muzzle velocity to be approximately 3.36 meters per second squared. Part 2, the angled launch challenge. Now we tilt the launcher to 30 degrees, 45 degrees, and 60 degrees. The velocity splits into horizontal Vx and vertical Vy components. Using trigonometry, we find our initial speeds for each direction. For a 30-degree angle, our Vx was 2.90 meters per second, and our Vy was 1.67 meters per second. Because the ball now goes up before it comes down, we use the quadratic formula to find the new flight time. We define our constants as A equals negative 4.9, B 1.6 meters per second, C, this changes based on the angle. For 30 degrees, it was 0.97 meters. For 45 degrees, it was 0.38 meters. And for 60 degrees, it was 0.40 meters. For the 30-degree shot, solving this gave us a flight time of 0.637 seconds. Then we multiplied this time by our horizontal velocity, Vx, to get a theoretical landing spot, xf, of negative 1.85 meters. Now we will be moving into the percent error. Finally, we compared our perfect match to the actual marks on the carbon paper. We calculated the percent error by taking the experimental difference and dividing it by our theoretical distance. Our errors were quite high, ranging from 98% for 30 degrees and over to 800% for 60 degrees. Why so high? This suggests a systemic error, likely involving how we establish the theoretical line on the floor or factors like air resistance that our formulas don't include. We see that while the math provides a perfect model, the real world has variables we must always account for. Thank you for tuning in tonight. And that is all for tonight's media coverage. I am Jade Salcedo, signing off.
Good evening. I'm Jeremiah, and the results of this experiment demonstrate the reliability of kinematic equations in predicting projectile trajectories. Though discrepancies were noted, our percent error calculations. These errors likely stemmed from atmospheric factors like air resistance and minor fluctuations in the spring loading mechanism of the mini launcher, which are not accounted for in the vacuum-based theoretical formulas. Additionally, slight inaccuracies in the manual measurements of the initial vertical position or the leveling of the projector could shift the data. To minimize these errors in future trials, using a digital photo gate to measure the YM more precisely and ensuring the launcher is mounted on a perfectly level surface would be beneficial. Our percent errors were not equal across all angles. Specifically, higher launch angles appeared to result in likely because a longer time of flight allows air resistance and wind to exert a more significant influence on the balls. I'd like to give a special thanks to Jade Salcido, Alexa Melendez, and Christian Perales. Thank you guys so much. This has been Jeremiah Alguin, and this has been a wild ride.